Alright, so today I'm going to be explaining this important paper with the title GraphCrop, Subgraph Cropping for Graph Classification. This paper in 2020 from University of Nanyang, Singapore. So we present a new method to regularize graph neural networks for better generalization in graph classification, observing that the omission of substructures does not necessarily change the class label of the whole graph. We develop graphcrop, data augmentation method, to simulate the real-world noise of substructure omission. In principle, graphcrop utilizes a node-centric strategy to crop a contiguous subgraph from the original graph while maintaining its connectivity. By preserving the valid structure context for graph classification, we encourage GNNs to understand the content of graph structures in a global sense rather than rely on a few key nodes or edges, which may not always be present. So, is parameter learning free? GraphCrop is parameter learning free and easy to implement within existing GNN-based graph classifier. Qualitatively, GraphCrop expands the existing training set by generating novel and informative augmented graphs, which retain the original graph labels in most cases. And quantitatively now, GraphCrop yields significant and consistent gains on multiple standard datasets and thus enhances the popular GNNs to outperform the baseline methods. So you see, the omission of substructures does not change the genre label action of an actor, Daniel Craig, in Ego's network. In the real-world movie collaboration datasets, node represents actor or actresses, and there is an edge between them if they appear in the same movie. Class labels of graph are the genre of the movies in which the actor or actresses collaborate. So if we, for example, crop from this side, or crop from this side, or crop from this side, different selection that you set, you have still the graph label is the same. That is the idea. So in the middle column, the connectivity from different nodes in the initial node is positively related to their color shades. This is the pipeline of GraphCrop. So we have initial node, and we have distance calculation. So from that we can create this subgraph. We call it subgraph cropping. And so this is example of subgraphs. By the way, this paper is very useful if you want to develop new kind of diffusion-based graph generation or any generative models for graph generation. This idea is very interesting. Example subgraphs that GraphCrop obtains from protein dataset. The original graphs are the odd-numbered columns, while the corresponding cropped subgraphs are on the right-hand side. The connectivity from different nodes to the initial selected nodes is positively related to their color shades. So when cropping a subgraph from original graph, we need to decide what nodes and edges to retain. We design our crop, just these 3 steps you can do this graph cropping. So we select a node very uniformly at random. Then we evaluate the connectivity of this node to we evaluate it. Then we select some nodes with highest connectivity to this V. For example, we select only these. And rho is a hyperparameter, of course, to adjust the size of the cropped subgraph. And we visualize the pipeline as I showed you. So since large graphs have more nodes than small ones, they can absorb more noise while maintaining their ground truth label. To compensate, we vary the number of nodes in the graph. To fulfill step 2, which is evaluating connectivity, we need to use a metric to evaluate connectivity between nodes. A simple metric is the length of shortest path. However, this metric does not necessarily change when connections or path between nodes increase, and thus it does not reflect the connectivity effectively. So we utilize diffusion matrix to measure the connectivity. This diffusion matrix. Of course, this diffusion and that diffusion and that, there are many concepts of diffusions that we should distinguish. So T is just a generalized transition, and we are working on the powers of that. The closed form solution to this personalized page rank diffusion is formulated like this. Graph diffusion is related to the random walk process. A large K achieves a sufficiently long random walk to gather enough information about the topology of the graph. So graph crop can be easily performed on CPU during data loading. The subgraphs given by Uninode do not have the original structural property. The sample nodes are in darker colors. So we have distance calculations around each node, and then we have subgraph cropping. So they did experiments on enzyme dataset DND, NCI1, NCI109, protein dataset. These are benchmarks for graph classification. So these are standard deviation of that, because they did experiments on 10 different seeds, and then this cross-validation. You see, if you compare graphlets or GCN to graphcrop, you see slight improvement. For example, if you use diffpool, which is a hierarchical graph pooling, it's almost the same as using graphcrop. Also, they use these social datasets like Colab, Reddit, and they compared again the same methods, the same baseline, like Graphlet, WL, GCN, diffpool, eigenpool, graph isomorphism network. If you compare a graph isomorphism network with graph crop, you see it's just 1% improvement. And also they did node classification. They did for node classification. Now they have here they have different subgraph sampling methods. Because your subgraph sampling could be either drop edge, uninode, or different versions of graphcrop based on personalized page rank, heat diffusion, and others. So that's it.